I'll have just charges jumping from one side to the other, and there will be bending of the bands and so on. Okay. Is it more clear, or okay? Any other questions? Yes. Next week, Thursday. I haven't decided the format yet, so yeah, I'll let you know. Okay. I'll let you know about the format. I just want to ask if everyone is okay with the date. Okay. Any other questions? All right. So last time we were dealing with something like this. We had a slab of material, as usual, and we connected a battery, and we had a ammeter here. Okay, and this side is also grounded. And then we had a voltmeter connected to the sides of the slab. Then finally we had a uniform magnetic field, let me name it BZ, going through the slab of material. And there will be a current flow here, which means my electrons are moving in this direction. Okay. And the question was, how would these electrons move under the influence of this external magnetic field? And we were interested in reading this voltage because I promised you that these two guys will give us the electron density eventually. So we were after measuring electron density in a system. And let me go through my notes just to make sure I don't skip anything. Okay. Now first, before attacking this problem, to obtain a relation between end and the applied parameters, I would like to introduce you something a little bit difficult to understand mathematically, but at least it would be nice to know why the assumptions we made in Drude model can be translated into a semi-classical transport equations. Because we'll be using mostly semi-classical equations of motions to describe the behavior of electrons in solids. And I'd like to show you that the very basic assumptions that we made in Drude model actually has deep relations to the semi-classical equations of electrons that obey. Now, so diffusive transport. This means length of my sample is much greater than the scattering length of the electrons. Okay? Now, the first thing that I assume is this. Neither full nor empty bands carry current. I mean, we have been using this for the study of metals and semiconductors and their junctions. This is what we have done. If you have a full band, it cannot carry, like the valence band in a semiconductor. And if you have an empty band, like the conduction band in a semiconductor, they cannot carry electric current. So we are limited to the regions where we have partially filled energy bands. Now, we can write down the semi-classical equation of motion. This is the wave vector, equals to minus E over h bar. I have E, then velocity. I'm writing it in terms of, as a function of k, so I'll restrict myself to the k space. It turns out that working in the k space is much more easier. By the way, these, I don't expect you to memorize the algebra. Just try to understand the idea that I present here, okay? That's much more important. If you understand the very basics of the equations, then you'll have an understanding about how really this k-space algebra works, and you can use that idea to understand the further concepts. Now, here I can write a few more things. So if you just consider this equation, this tells us that resistance of a perfect crystal vanishes, but resistance comes, I'm sure, comes from the interactions. I think this is worse. Okay. So, for small electric fields, applied, only a small fraction of the electrons around the Fermi level, I should say Fermi energy, contributes to the current. Okay, so I have two or maybe three basic assumptions when I'm going to drive the equations. So let me get rid of this. Now, I'm going to write down the Boltzmann equation. So, if you consider the Fermi Dirac distribution, this is what we have, okay, divided by kBt. And I also have a minus sign here. But this is true when my system is in equilibrium. Okay, so this is in equilibrium. But when I apply an external force to my system, I destroy this equilibrium condition. So what I'm going to get is a new distribution function, which is a function of k, r, and t. Okay, I can say this is my electron distribution function. And this function will determine the distribution of electrons in the K space. So now I'm going to have, if you consider this sphere in the K space where I had like Kx, Ky, and Kz, then this distribution would tell me how my states are evolving with time in this K space. So the number of electrons will simply be given by this integration then. Okay, so if I integrate this element, then I'll get the number of electrons. And of course, since I'm dealing with electrons, I'm considering spin 1/2 particles. So that's why I have an extra 2 here. I can put 2 states in a single energy level. Now, please bear with me. This torture is going to end very soon. Now, let's say after some time t, after applying the magnetic field, what I'm going to have is going to be something like this. So if I consider this K and R, this K will be displaced by a displacement vector, and my position will be changed by a displacement vector. So this is some delta t after some time t, okay? And this change will be something like this. That's E or h bar, E dt. Then my r will be changed by some velocity times dt. Okay, so this is a small change. Basically, what I'm telling here is this. I have an electron in real space. After some very short time interval, delta t, okay, very short time interval, delta t, my electron moves by this much in the real space, velocity times the time that it takes, okay? So that makes sense. And if you look at the phase space, then its k value changes by this much, which also makes sense because the applied electric field, if you look at here, so ignore magnetic field for now, applied electric field times the that small time interval, delta t, will correspond to that small change. Okay, so this is electric field, not energy. So what this equation tells me is that in K space, because of this force, K value will change by that much. So nothing fancy, nothing complicated. Now, this distribution function will also change because of these changes. Okay, so this change can be simply written as the time derivative. So I'm looking at the scattering events, basically, times delta t. Now, let's put everything together to show how the distribution function will evolve in time. So this guy, K minus E over H bar, electric field times dt, R plus Vk dt times T plus delta T. Again, I have this dk dr is going to be equal to K plus, oops, not plus, I'm sorry, K R T dk dr plus that scattering event, so dk dr dt. Now what I have done is this. I have a function, a distribution function, that defines how my electrons fill each individual energy state. Then I look at a very small change within this distribution, and I write that small change in terms of time delta t after delta t, the initial starting distribution function, plus the change that's caused by the scattering event because of the external force. So if you physically consider what's going on, I have an electron with a certain energy, with a certain velocity, okay? So we are looking at pretty much free electrons here. And under the influence of the external electric field and the scattering events, it's going to change its velocity. So what I'm interested in is that infinitesimal change after time delta t. So what I write down is the initial distribution function, which defines its initial parameters, plus that scattering event that resulted in electron to move from here to here, which will be equal to the distribution function that is delta t after. Now this equation will basically give us the solution that we are after. So this guy is called, what I'm going to write down is called general Boltzmann equation. So first I'd like to introduce you this. If you have a function fx, you can write it as a series of functions around a certain point, okay? Factorial x minus a squared. And then x minus a to the power n. So if you take a function and look at it around a certain point where it's well defined, like You're right. So this is A. This is x minus A. Okay? So that follows the logic. I mean, if you look at this general formula and sum it over all n values starting from 0 to infinity, then you can describe a function around that point A. So this is Taylor expansion or Taylor series. Okay? And now if we do the same thing for this distribution function, for the first order in dt, so this general Boltzmann equation is a first order expansion in dt, okay? So what we can write down is going to be this. So I have v dot ik r t minus e h bar dot, of course. So for k, I think I forgot a k here. Or t plus del t equals to del t scattering. Okay, so I'm only interested in terms up to the first order. Get rid of this part. So now I can introduce one more thing. My distribution function can be written like this. Let's start with the Fermi distribution. Okay? And what I'm going to do is I'll define some relaxation time, tau, which you can call scattering time as well, which means my electron, if it starts a motion under the influence of the external electric field, it will on average take time tau before it finds another scattering event. So once it scatters from a scattering center, it will have tau time to follow the electric field. So the relaxation time defines basically the time that it travels without any scattering event. So it's the tau that we defined in our Drude model. It's the same quantity, if you like. Okay? So what we do is then I'll define this guy minus fk is going to be e times tau over t. So this function, this formula basically tells me initially I started with a Fermi distribution because my system was not under the influence of any external forces. Then after time t0, it assumed a certain distribution, which the difference between this initial Fermi distribution times an exponential decay factor, which is determined by this relaxation time, will determine the distribution at time equals to t. So from this expression, this assumption, I should say, I can write down that the scattering event, so this time derivative at scattering event, will be equal to IKT minus FK divided by tau. Now, there's only one more thing left to show that actually we are, the results that we have is going to be similar to the Drude model. So, if I write this down now, the final equation, I end up with something like this. So again, this is an integral over k. So this must be k minus fk divided by tau. So if I reorganize everything, we'll end up with an equation like this. Tau e over h bar. So the final distribution function is the Fermi-Dirac distribution plus this modified term. Okay, that's because of the electric field. So if there's no electric field, no external forces, my distribution function will be equal to the Fermi-Dirac distribution. So now let me show you how we end up with the Drude model. Now, if we assume that we have only a very small displacement in the Fermi sphere, so I'm considering again my free electron gas, and I'll only look at a tiny displacement. I mean, it can be any direction, by the way. So this displacement should be much smaller than my k vector. That's kf vector. So E tau E over h bar should be, I should say, much smaller than kf. If I satisfy this condition, then it turns out that I can write down this as such. So f k plus E tau E over h bar. And this is the simplified Boltzmann equation. Yes. Sorry, what? This one? Yeah, of course. Because both sides of the equation are scalars, so. Again, this is a vector quantity, right? So you must dot it with this vector quantity. Okay. Now, there's one final thing that is left to be done. Now, by using the simplified Boltzmann equation, I should be able to derive, because now I made the exact same assumption that I made with the Drude model. I ignored the microscopic details. I'm looking at my sample size L that's much greater than the scattering length. And then I confine myself to the case where this effect of the force is much smaller than the kf. So I should be able to derive, if you like, the results that I got with the Drude model. So what I do is, let me write this down first. This was the expression we defined. So for any external electric field we apply, the current density we get is proportional to the conductivity. So current density can be written as sum of all contributions coming to the JK from all the states. Okay. And I'm not sure if I should write this down. What you need to do is basically, let me write down the first few lines of the solution. So this is what we get. I have K, then my Fermi distribution, dk, plus K, Fk, again there's a dot here, tau E, H bar, dk, okay. And then if you play around with this equation, basically this is what you end up with, minus E squared tau H bar squared divided by 4 pi cube m squared integral K del F K over del E, and you have K dot E here dk. Now this may look like an alien to you, but after playing around with that equation a little bit more, so I can write down conductivity as such, if you like. So I have my J vector, okay, current density, and I would like to write this expression in terms of sigma. So what I would like to do is replace this guy. So I'd like to write an expression for sigma in terms of J. So what I do is basically this. Okay. So if I dot J with E, I'll get the magnitude of E on this side. If I divide both sides with the magnitude of E squared, then I'll end up with my sigma. And if I put that expression in here, that integral expression, that's what I'm going to end up with. E squared tau H bar squared 4 pi cubed m squared integral K dot E squared E squared dfk dE dk. Okay, so what are we looking at here? If you take this guy and say, by the way, I'm sorry about this, this leads to a confusion. Here, this E is energy. If you don't see a vector sign on top, it means it's energy, okay? So at sufficiently low temperatures, and if you like, this was a final assumption in Druid model. We didn't have any temperature expression. This expression will turn into something like this. Del F del E will be EF. And this is a Dirac delta function. Let me explain what it is and what it looks like. So at low temperatures, my Fermi Dirac distribution looks like a step function, okay? So this is called a step function. Now, if you look at the derivative of this function, this is my energy, this is my f function. If you look at derivatives of this function with respect to E, it will be 0 on both sides of this function. But here, right at EF, it turns out that this del F del E, so if I draw, so this is my EF, becomes a function like this. So it only has a value at EF and nowhere else. So it's only defined at EF. Okay? So then I can also write this down as such: m h bar squared k minus kf. So if you like, I removed, so E is h bar squared k squared over 2m. So I removed this expression to be able to write it down in terms of this k function. Now, if I plug this back into this expression, then the integral will only survive at this kf point. Okay? So if you take an integral of this, then the result you're going to get is going to be kf. Okay? So it's only defined at that point. So if I do the same thing here, this is what I'm going to end up with. Square tau 4 pi cubed m. Let me write this integral down one more time. Okay, minus kf over k dk. Then, finally, if you do the integral and get rid of everything else, this is what you get. So sigma conductivity is E squared tau kf cubed divided by 3 pi squared over m. Now, this expression is actually extremely familiar to us. Let me continue from here. Because n is density of electrons, is 3 pi squared kf cubed. So if I replace this expression back in there, this is what I'm going to end up with. Sigma equals to n e squared. Oops. Sorry, I messed it up. N e squared tau over m, if you like, n e mu. That's mobility. And if you remember, this is the result that we derived from the Drude model. So this whole exercise was rather too complicated. I accept that. But we started with a general distribution function under the influence of an external force. And by doing some algebra about its motion in the k-space, we ended up with a result that we derived for derived with our very basic assumptions on a classical free electron gas. So in a way, this theory is more comprehensive than the Drude model. So by simplifying it, we could reach the very results of the Drude model. So this is a semi-classical approach, and I just wanted you to have an idea about how we justify the use of semi-classical equations of motion in our coming studies. Mm-hmm. Yes. Mm-hmm. Well, yes. I mean, the very idea, I mean, if you consider this, we are writing down a force equation, but we are representing it with this k vector rather than a physical momentum. So you're right. We switch to a k-space where we define with Fermi-Dirac statistics, and then we do the rest of the calculation based on that statistical model. So that's the quantum part, if you like. We do the counting using quantum mechanics. But then we use force equation to understand how that counting changes in the phase space, rather than really solving a Schrödinger equation or by applying another full quantum approach. Yeah. This one? So in this case, we got contributions coming from all k points in the phase space. Okay, so then the distribution of j's within the k space is determined by the strength of the electric field and the k function and the Fermi-Dirac function. So what I do is I write an expression for j. I think I skipped that part, but you can write j as, let me check my notes not to make a mistake. So you can write j as I haven't written it down, but let me see. Let me check the book because I don't want to make a mistake. So sorry, it was here. Yeah, yeah, exactly. So, I mean, here is the full expression, if you like. So we have minus E phi k Vk, and I can write this down as minus E h bar over n k phi k, and then this is this, but I can write this down as a expansion in Taylor series, so k plus this multiplied by this guy, so I get two integrals, but I didn't want to write it down since really the details here are not too critical, at least for the sake of this course. Of course, if you're really interested in, I strongly recommend you to go to the chapter 2.6 of this book, and you can find full derivation of of this whole stuff. It's Mesoscopic Electronics and Solid-State Nanostructures. This is one of the recommended textbooks. Okay, so 2.6, chapter 2.6. Any other questions?
So this was
No, no, no. That's,
so we try to actually sort of variation parameterizing that.
exactly.
We try to find space variation and time variation.
Exactly.
And we equalize both them.
Well, we actually did, we under the influence of this external force will both have a time variation and a space variation, which inevitably results in a shift in the K space. Okay?